thank you for the invitation. I wish I were there. And actually, yeah, so I guess after the fact, I'm happy that I didn't go because this country went on strike, the airlines. I would have been stuck. But anyway, so it's a pity that I can't be there. I'm going to be talking about a paper that has a couple of years now. It's a paper with joint work with George Andrews and Jethro Van Ekeren. And yeah, so I guess probably it's not the right choice of subject, but I'm going to keep it in really elementary just for like undergraduate students. That's one advantage. The disadvantage is that there's no geometry. So at least I'm going to give a little bit of geometry now, which is the actual question, which is the only thing that you should take out of this. And it's the following. Say you start with some polynomial algebra or some affine Poisson algebra. It's going to be in the end, but the example that I want to take in hand is just this guy, or probably this guy. Just so this is just a fat point or just the affine line. So this is just x to the s, and s is just some natural number. And this is a commutative algebra. In general, it's going to be a Poisson algebra. You can view this as a Poisson algebra with a zero bracket. But the point is that I want to take the arc space of that guy. So let me call this guy R and JR. This guy is going to be a commutative Z plus graded algebra with the derivation is a differential algebra of degree 1 and generated by R. So in degree 0, this guy here is a direct sum like this, n bigger or equal than 0, and in degree 0 you just have R. And it's freely generated as a differential algebra by R. Namely, if you have any other algebra with these properties, then that's going to be a quotient of this JR. And in this particular case, which is the only case that I care about, this is very simple to construct. This JR, if you didn't have the quotient, it would be just simply C of X, its derivative, its second derivative, this is the formal guys, and so forth. So it's infinitely many variables. Here, the derivative of X with n lines in it, well, let's say X is just X line, and the derivative of X line is X second line, and so forth. But since I have this quotient by X to the S, then I'm going to divide by the differential ideal in this differential polynomial algebra generated by X to the S. So here, this ideal is generated by X to the S, the derivative of X to the S, and this, you guess what it is. This is just S times X to the S minus 1 times X prime, and so forth, and all the derivatives. Okay. So that's explicitly the arc space of this fat point. And in general, I'll be interested in what happens when you have other Poisson algebras. I haven't used the Poisson structure, and we will never use it in this talk, the Poisson structure in R. But in general, what happens is that if R has a Poisson structure, so if R is the algebra functions on a affine Poisson variety, then JR is a Poisson vertex algebra. So it is the classical limit of some vertex algebra. Actually, that's probably, I'm not even sure if that's a conjecture. There are Poisson vertex algebras that are not limits of vertex algebra. So it might not be quantizable. But every example that I have, it's going to be like this. So another example that you should have in mind, which I know nothing about and I would love to have, is if you have, we could do this for any Lie algebra, but I'm going to be explicit. I want to have polynomials in 3 variables. EHF. So this is the usual Poisson structure on SL2 star. And I want to divide this by the Poisson ideal generated by the Casimir times E. And then, well, I just gave you a description explicit of what this JR is. So it's an explicit description as a quotient of a polynomial algebra above. You just take a non-Newtonian algebra generated by infinitely many variables, which are E, H, and F, and all of their formal derivatives, and you divide by this guy and all of their derivatives and all of the Poisson brackets of these guys in this Poisson algebra. This one is an example that doesn't have a trivial Poisson bracket. Okay, so this is everything that you need to take from this talk. If R is finite dimensional, as are these examples that I chose, if it's not, then just take the fiver at a point on your Poisson algebra. But if R is finite dimensional, then this JR is a direct sum of finite dimensional pieces. And these guys are finite dimensional. And it makes sense to compute the character. So the character of this JR is the sum of Q to the N times the dimension of this jet space, the nth jet space of R. And question, what is this function? Question, what is this function? It's incredibly hard to compute this function. And there are some beliefs that this function has nice properties when you use the Poisson structure in R, therefore the Poisson vertex algebra structure on JR. It's really, really hard to compute this function to the point that the only example that I know is the example that I started with. So only know this. And it's a recent paper. Well, not anymore, but it's less than 10 years paper. This, in the case, C of X divided by X to the S. So the fat point. So this is how complicated this problem is. It's a very hard problem to compute the graded dimension of arc spaces. Yes.
Like the definition of R above. I mean, you have this polynomials and free variables quotient. So
yeah.
So it's EHF quotient by what?
Oh, so this is going to be, you take the Casimir and you view it as a quadratic polynomial. So it's just E times F plus H squared plus F times E, normalized some way, and just multiply that by E. So now it's a polynomial of degree 3. And you take the Poisson ideal generated by that inside of this the dual of
the Poisson ideal. So
sorry, just take the Poisson bracket of that. So okay, so let's remove the Poisson here. And let's take these three generators, omega E, omega H, omega F. That's it.
I see.
So if you want another, so for people that know over vertex algebra, this is the C2 quotient of alpha in SL2 at level -2/3, if I'm not wrong. So it's the first, it's a boundary admissible level, the trivial boundary, the first boundary admissible level of SL2. That's the C2 quotient of that. In general, if you take omega times some power of E, it's going to be on a boundary admissible level. And I know nothing about this arc space, and I would really want to know this. I'll mention higher chiral homology, but towards the end of the talk. So this, I would love to have the graded dimension of this algebra. This very explicit algebra. And I think this is a very hard problem. And I think that's the easiest example besides what I just gave here. So this, the graded dimension of this fat point is a recent paper of Bruschek, Murtada. I'm not going to write this correctly. Murtada and Shepers. And I never remember if Shepers has a C or not. Where they computed this by finding a Grobner basis for the ideal. So the basic technique is to look at this as a quotient of C of X, the first derivative, and so forth, divided by an ideal. This is the ideal I, which is generated by x to the s as a differential ideal. They found a Grobner basis for this ideal I. Let me just, the idea is find a Grobner basis for I. And once you find a Grobner basis for I, you get a nice basis for the quotient counting partitions. So you convert the problem of finding the graded dimension to a problem of counting partitions. And they solved the problem of counting partitions. They counted this, they found the generating function for the partitions that are given by this Grobner ideal, the leading monomials of that Grobner basis of this ideal. And they found explicitly the generating function for this guy here. And that, I'm going to write it in a second what that function is. All right. So that's the only example where we know. And this is the only thing that you should take off this talk. It's hard to compute generating functions for arc spaces. All right. Since I said Rogers Ramanujan identities, let me just tell you what these partitions are. So a basis, I'll tell you in a second because I want to use a different notation in a second. So now today's talk. And I'm going to get back to this Grobner basis in a second. Today's talk is going to be about the Virasoro-Lie algebra. So we're going to have the Virasoro-Lie algebra. Save here. This is an infinite dimensional Lie algebra with these brackets. And then here you need to multiply by m cubed minus m. And C is central. And I'm going to define this. Just pick a complex number C in the complex plane and define this guy. Where C is going to be the induced module from a one-dimensional representation with one vector to the whole of Vir from Vir plus, where Vir plus is the linear span of Ln, where n is bigger or equal than -1 and the central element. And C acts on the vacuum vector by multiplication by C, and Ln kills the vacuum vector. So that's the one-dimensional representation of this subalgebra. Induce it. That's the vacuum module. And this is going to be the Virasoro universal algebra. This is the universal Virasoro vertex algebra. It has a vertex algebra structure, but it's an explicit description. We have an explicit basis. It's very clear by the PBW. It's a PBW basis. And it's given by guys like of this form. And let's put N1 minus N2, L minus Nk acting on the vacuum with the condition that N1 is bigger or equal than N2, Nk, which is bigger or equal than 2. So we have an explicit basis for this guy given by partitions with parts bigger or equal than 2. And I need to put 2 here because I declared that L minus 1 kills the vacuum. All right, so we can compute the character quite easily. We know a lot of things about this guy, but what happens is that when C is a particular rational number, it's of the form P minus P prime square. I hate formulas, so probably I'll get these guys wrong, but I think this one is correct, where P and P prime are co-prime numbers, and P is bigger or equal than 2, then this module, Vir C, has a unique singular vector mod up to multiplication. vector v pp prime, and it generates a submodule, and that submodule, if you quotient it out, you get a irreducible representation, which is the minimal model for that central charge. So the quotient, where C is the quotient of this universal guy by the submodule generated by that vector. Okay, so we had a PBW basis for this that was explicit. This guy inherits the same filtration, same PBW filtration. According to this, if we choose an order for the basis, you're going to get an order. You're going to get a basis for this module, and that's the basic question that we have since, I guess, the 70s. Question: what is the PBW basis of Vertex? It's a very basic question about a module that is a minimal module of central charge C that we have been studying this for over 50 years now. We should know the answer to this question. And the answer is we know nothing about this.
Raimundo, I'm a little bit, I have a question. I'm a bit confused. So you're saying there is only, it's sufficient to quotient just by one singular vector. For minimal models, there are not always like a pair of them. I just, maybe it's a wrong memory, but just.
So if you quotient by this guy, you get an irreducible module. And that's it. So the thing is that these are very special ones, which have H is equal to 0. If you're looking at arbitrary Verma modules for the Virasoro algebra, the situation is different.
Okay. So like it's even among minimal models, that's a special one, right?
Yes, that's correct.
Okay, thank you.
So yeah, so in general, I shouldn't be doing this thing of like inducing from this verb plus. This is very special that the vacuum has weight 0 and it's scaled by L minus 1. In general, you would ask for a weight for L0, which is non-zero, and then L minus 1 is going to act in a different way. So in this particular case, the Verma module has L minus 1 of the vacuum as a singular vector, and you already killed it. But it's this kind of questions you can guess that it has been studied, and indeed there are some results which probably here people know better than me, so I should ask. I should have asked Edward a long time ago why this paper hasn't been published, or I couldn't find the reference. But Fagan and Frankel have a paper in the 90s, I think it's 93, where they do this, compute this. For the case P is equal to 2. And then P prime has to be an odd number. And the paper is beautiful because they use conformal blocks. They have this beautiful paper where they compute this PBW basis. What they end up proving is something that in today's language is the fact that these minimal models are called classically free. I'll mention that in a second. And they do this before Murtada, Prushek, and Shepard's paper. I'm going to rederive this using their paper. Now it's a triviality given Murtada's work. But this paper is beautiful using these conformal blocks. And as far as I know, this paper hasn't been published. And there's nothing done. So in today's talk, I'll describe the situation. P is equal to 3, P prime is equal to 4, and therefore C is central charge 1/2. And this is the paper with Andrews and Varnekeren and myself. So, and nothing else is known, no other case. It's remotely known. We have no idea about any other case. More than the problem itself of describing the basis, I want to tell you how I got to the problem, because the basis itself is not interesting. The method to prove it is not interesting. What's interesting is why we care about this problem itself, why we care about the problem having a solution. But anyway, so the problem has been explicit. And now I want to tell you how to solve this problem. Okay. All right. So let me tell you a little bit about the case of P is equal to 2. So what do we know about these minimal models as I described? So first of all, remember the basis. The basis was given by linear combination of vectors like this in the universal case. N minus 2, L minus K applied to the vacuum. This guy has a conformal weight, has a degree. This is a graded module. The degree of V is the sum of the NI's. So this is a graded module. And the singular vector is homogeneous. This unique singular vector VPP prime, what I know is that it lives in degree P minus 1, P prime minus 1. And let me write this guy as S. So this is the definition of this S. That's not all that we know. We know this. So what's a vector in that degree? Well, we know this is a vector. L minus 2, L minus 2 of the vacuum. How many times? Well, S over 2 times. So this vector is of that degree because the degree of each one of these guy counts as 2, and this S over 2 makes sense because these two numbers are coprime. So this product S is even. And then anything else that I put has to be lower in the PBW filtration. This is the partition that has the most number of parts for that degree. So lower terms, PBW terms. Any other partition of this number S in parts that are bigger or equal than 2 should have less parts. And there's nothing more that we know about these singular vectors. So not only we do not know anything about the graded dimension of arc spaces, we don't know nothing about basis, PBW basis for these modules. We also don't even know what are the singular vectors. There are formulas for P is equal to 2. I think there's closed formulas for P is equal to 3. There are recursive formulas in general, but I think there's no more closed formulas than the ones that I mentioned. I might be wrong on that. But it's certainly not known, this VPP prime. What I am stating in this statement here is that the coefficient of this monomial is non-zero, and that's all we need. So the leading PBW term that can happen at that degree appears in this singular vector. That's the only important statement here. So this vector, when I pass to the associated graded with respect to the PBW filtration, is not going to be 0. It's going to be equal to that guy, to this power. Okay. So that's all that there is there. Okay. So now I'm going to look at the associated graded. Let me just tell it like this. A is going to be the associated graded here, C. With respect to the PBW filtration. This associated graded with respect to the PBW filtration. I'm going to change this a little bit. Okay. But we know what it is. Okay. So this is a quotient. Let me tell you something. So we know that we have a quotient like this. We have L minus 2, L minus 3, and so forth. So it's an infinite polynomial algebra. So this is going to start to look like an R space. By this observation here, in the associated graded, this vector here is equal to just this power. Everything else is lower in the PBW filtration. So if I kill that vector, this guy is going to be killed. Now, this is a differential algebra. Del of L minus n is equal to n L minus n plus 1. And I'm going to take this. If this vector is 0, then all of the derivative is 0. So I have a surjection from here to here. This is the free algebra, the free differential algebra such that this guy is 0. So this surjects into A. And this is the second question that I have. So second question, this is a question of Arakawa in general and Moreau. So is this an isomorphism? Let me phrase it in terms of vertex algebra theory in general. What's going on here? This guy here is a vertex algebra. Every vertex algebra comes with a filtration, and the associated gradient is a Poisson vertex algebra. This quotient here, this algebra here, let me call this algebra B. What B is, oops, something crashed. Let me see. Let me see if I can recover this. I think I can. Let me try to share my screen. I think we're back online.
That looks great.
Great. All right. So this algebra B here is a jet algebra. It's an arc algebra. It's the arc algebra of a fat point, as I described. Okay. So what's the situation? This fat point is the C2 quotient of the Virasoro vertex algebra. It's this polynomial algebra, modulo this ideal. You take the arc space of that, so that's the free algebra generated by this polynomial algebra, and you're asking whether or not that is the associated gradient to your vertex algebra. So let me write this. So if V is a vertex algebra, any vertex algebra, R is its C2 quotient. This is Jou's C2 quotient. This is a Poisson algebra. You have two different Poisson vertex algebras associated to that. You can consider both of them as a classical field theory associated to a CFT. One is the free field theory, which is the arc space of this Poisson algebra. So this is a PVA. So that's a free algebra generated by the C2 quotient. And the other one is the associated gradient with respect to the standard filtration of V, which is called the Lie filtration. So that's a classical limit of V. This is also generated by R as a differential algebra, but this may not be freely generated. So this always you have this surjection, and the question is it an isomorphism or not? So this was a question that was asked, perhaps wasn't asked, it's just that we didn't have examples where this wasn't an isomorphism, and Tomoyuki was asking around if we had some example. And the first example is a theorem of Van Ekeren and myself, which is not really a theorem, it's just an observation. It should be a theorem of Fagan and Frenkel. It's that in the case of C, it is an isomorphism.
Is there a unique classical limit always, or do you need to choose some extra data to define that?
So that's a good question. So let me give you a definition of classical limit so that we can talk about being unique or not. So the question here is, if you give me a vertex algebra, I will declare a classical limit to be a filtration of that vertex algebra, such that the associated gradient is naturally a Poisson vertex algebra. And the multiplication should be the normally ordered product on the vertex algebra, and the Poisson bracket should be the OPE of the vertex algebra. So I do not know if there are different filtrations that would lead to different Poisson vertex algebras. For vertex algebras, if you have a conformal vertex algebra, there are two natural filtrations. And there's a theorem of Arakawa that shows that both associated graded are isomorphic as Poisson vertex algebras.
Awesome.
There doesn't seem to be the case that we have different classical limits for a given vertex algebra. But there are different definitions of classical limits. So if you're looking at families of vertex algebra, it's a different thing, with a special fiber being commutative. So my definition doesn't seem to give you different classical limits. Okay, so what happens is that the associated graded to the Virasoro minimal model is not classically free. It's not classically generated, freely generated. So it's only true when P is equal to 2. So we know that we have a natural kernel in this surjection that I wrote there, that I'm going to write it again. So you have a polynomial algebra in L-2, L-3, and so forth. And you divide by L-2 to the S. And this surjects into this associated graded to Vir C. And the kernel is non-trivial. This is a differential ideal. That is non-zero if P is different than 2. So I'm going to start calling vertex algebras classically free if this surjection is an isomorphism. And we know a lot about chiral homology of classically free vertex algebras. It's just that we do not know when a vertex algebra is classically free. So we know, for example, that for affine Kac-Moody algebras at integral level, this is an isomorphism. We know that for affine Kac-Moody algebra, well, we know that for SL2 at admissible level that is not boundary, this is not an isomorphism. And I know nothing about the boundary admissible level. That's why my question about that particular quotient of the polynomial algebras in E, H, and F. Okay, so now that I have this, I can ask a question that Andrew Linshaw has been asking around, which is I finitely generated as a differential ideal? And here comes something surprising, because we have been working, or many people have been working on this for a while. And so an observation is that there is no example, no counterexample, which is not artificial. So not for this, but for an arbitrary vertex algebra. You take the free algebra generated by the C2 quotient, or you take the associated graded, the classical limit. This surjection, you ask whether or not the kernel is finitely generated. Put in a different way, if you take spectrums, what you're asking is the spectrum of this is defined by finitely many equations in the arc space. And there's no counterexample on vertex algebras, but there are many on arc spaces. So there's many of examples where you can set up this with this object here not being a vertex algebra, but just being a differential commutative algebra. And you can cook up immediately infinitely generated differential ideals coming from surjections like this. So here, I don't want to state it as a conjecture, but there seems to be something going on with the fact that you started with a vertex algebra, or at least with the fact that you have Poisson vertex algebras in these surjections, that these are classical limits of CFTs. So it seems that the fact that you started with a vertex algebra here and it gives you a Poisson vertex algebra here, that this surjection here is a surjection of Poisson vertex algebras, makes this I to be finitely generated. Let me tell you why I care about this question, and this is exactly why I came to be this. This is a theorem. So again, V is a vertex algebra. So there's two components here. We have R, which is the C2 quotient, is a Poisson algebra. we have JR mapping to A, which is the singular support, this associated gradient of V, which is a surjection. Let me call I the kernel. So if the Poisson homology of R, now that this is a Poisson conference, is so finite dimensional, and I is finally generated, then the chiral homology. So these are the DG versions of conformal blocks that were essentially hinted in the previous talk. So chiral homology of an elliptic curve, any elliptic curve with coefficients in V, is finite dimensional. You should take this as some generalization of Joux's theorem. So what is the chiral homology in degree 0 is conformal blocks. And Joux's theorem says that if R is finite dimensional, so that's V in C2 cofinite, you have finitely many conformal blocks. Actually, you can strengthen that. HP0 is R divided by commutators in R. And this is still true. If this is finite dimensional, then you have finitely many conformal blocks on a vertex algebra. So that's a particular particular case of this Joux's theorem, and it's a particular case of this theorem here. That's why I really care about this I being finitely generated, because we have no examples. And it took us a long time to prove the case where I is finitely generated in the unique example that we have, which is C is equal to 1/2. So I still have like 20 minutes, so I'll tell you how to prove that. So the theorem is that for Vir 1/2, I is finitely generated. Okay. So here's, okay, let me give you ingredients as to how do you get by this. Okay. So first of all, Murtada's theorem, Bruchek, Murtada's, and Shepard's theorem. Okay. So the first observation is, remember, this I is given by this quotient. Oops. The differential quotient of this. So Murtada's theorem says that I'm going to change now a little bit the PBW filtration. So I'm going to put that the degree of L minus 2 of L minus n, instead of being n, I'm going to put it to be n minus 2. So that this guy is in degree 0. And the whole, this is the arc space of something in degree 0. The degree 0 piece is now, P0 is this. Okay, so Murtada's, Bruchek, Murtada, and Shepard's theorems states the following. It states that the basis for this space, a basis, monomial basis, is given by partitions where every part bigger or equal than 2. So if you give me a partition, you're going to put something like minus n1 up to L minus nk. All of them are bigger than 1 and bigger than 2 that we needed before. But now you're going to ask that ni minus ni plus s minus 1 is bigger or equal than 2 odds. And these partitions appear in the Rogers Ramanujan identity. So these partitions, you know how to count. So the generating series for this partition is given by an infinite product. And this comes from Rogers Ramanujan's type identities, where this is mod S. Oh, actually, here is S over 2. And here is modulo S plus 1. All right, so that's the character of V. This is the graded dimension of V. And that's their theorem. And you know what is the character of the Virasoro algebra. So this happens to be, remember, this S is P minus 1 times P prime minus 1. So this thing here is the character of a Virasoro. So this is your C. But only when P is equal to 2. And since for every number S, you can find P and P prime that give you that number, that means that this character of P is only going to be possibly equal to a character of a Virasoro when P is equal to 2. And it cannot never be when P is equal to different than 2, because two different Virasoro modules have different characters. So that's how we know Frenkel's theorem now, because we know that this character, you have a surjection from P to curve vector C. We have the surjection, and we know that the characters are the same if and only if P is equal to 2. Therefore, this is an isomorphism if and only if P is equal to 2. So that's how you recover Frenkel. So we know that we're looking for at least one element in B that is not, that gets killed here. Okay, so now we have the characters of both sides. We have the character here. This is hard. So we're using a hard theorem, which used finding a Grobner basis and counting partitions. So the hard theorem here from geometry was we have the character. The easy theorem from representation theory is we have the character here. This is always easy. So we have the characters because we know the characters of irreducible modules for Virasoro. So now when you found this hard one, you just compute it, put it in a computer, and ask when is the first time that they're different. It turns out that in degree 9, they are different. So from now on, I'm going to fix. So from now on, C is equal to 1/2, P is equal to 3, P prime is equal to 4. And the character differs in degree 9. So in degree 9, there's something in the kernel, and it's of dimension 1. And yeah, I do not know how to find these things. Certainly, probably this computation, you can do it by hand. I wouldn't do it. Because anyways, the problem doesn't have a solution without computers. But you put it in a computer, the computer spits up immediately what is something in the kernel, and it's this. It's L minus 5, L minus 2 squared, plus 6 times L minus 4, L minus 3, L minus 2. So this guy is in the kernel. Remember, we also had something that we killed already, which is L minus 2 to the S. In this case, S is 2 times 3, which is 6. Oops, over 2. We should have killed S over 2. Yeah, well, yeah, no, I think that's good. That's correct. So we have these two guys that get killed, and the theorem, the explicit theorem is this theorem. The associated graded to Virasoro at central charge 1/2. This is the Ising model. This is the even part of the free fermions. Is isomorphic to an infinite polynomial algebra divided by these two guys. and all of their derivatives. Okay. So how do you prove this theorem? Again, the same technique. And this is the problem. I haven't learned anything. I spent a year trying to count the partitions that appear, and I haven't learned anything. So I'm hoping that someone smarter than me would do this for other modules. So same technique as Prusek, Murtada, and Shepers. Find a Grobner basis for this idea. Put in a computer. Find a Grobner basis. For the ideal generated by these two guys. Right, so this is a very simple statement. You have a graded polynomial algebra. These guys have positive degrees. You have these two guys, one in degree 6, the other one in degree 9. You take all of their derivatives and you ask a computer, stop at degree 30. What are the leading monomials of a basis for this ideal? And the computer would speed up. What are those guys? If you're looking at leading monomials, that's going to give you partitions. And then you look for patterns in those partitions. And it turns out that you find them. You find them immediately. So let me tell you what are the patterns that you find. I'm going to need a whole page. So these are going to be partitions. So let's see if it's clear. So these are going to be partitions of this form: L n minus 1, L n minus k are going to is the generic partition. So this corresponds to a partition where you have n1 like this. Okay. And I'm going to say that it avoids a partition, for example, the partition P, P, P. This means that you cannot have the same part 3 times. So if I read this, it means that I cannot have L minus 2, L minus 2, L minus 2. I cannot have L minus 3, L minus 3, L minus 3. And I cannot have P plus 1, P, P. And I cannot have P plus 1, P plus 1, P. And also, I cannot have P plus 2, P plus 1, P. So I cannot have 3 consecutive guys. And I cannot have P plus 2, P plus 2, P. And I cannot have P plus 2, PP. So if you think about this set of conditions, this is something that I've already written before. This means that every part is bigger or equal than 2, and everything P is bigger or equal than 2. And here I need P is bigger or equal than, yeah, that's fine. Here P is bigger or equal than 3. So these conditions here mean I cannot have a part which is equal to less than 2, and the difference between one part and the one that is 2 apart is at least 3. This is the condition that appears in Rogers identities. Identities. And these are the partitions that Prusek, Murtada, and Shepard's found. And this is because I'm quotienting by A. And A was this L minus 2 to the 3rd. So the new guy that we found is this B. And that gives other partitions that you should avoid because it gives you new elements in the ideal to which you're asking for a Grobner basis. So the partitions that you should avoid are P plus 3, I have 8 minutes, P plus 3, P, P plus 4, P plus 3. Oh, here these are length 4, PP, P, P, and the same thing here, P plus 4, P plus 3, P plus 1, P, I'm sorry for writing this is just in the sake of completeness, P plus 4, P plus 4, P plus 1, P. I just want to show how horrible these kind of things are when you put them in a computer. So what happens is you ask for what are the leading monomials on a basis of a polynomial algebra. And you recognize that you find the variables and you find the next. So if you find L minus 2, L minus 2, L minus 2 in the ideal, and then you also find L minus 3, L minus 3, L minus 3, and you find L minus 4, L minus 4, L minus 4, when you stopped at degree 12, that's the last one you find. And then you guess, oh, then probably L minus 5, L minus 5, L minus 5 is going to be there for every degree, and L minus 6, L minus 6, L minus 6, and L minus n cubed is going to be there in that monomial basis. The same for these guys. You just find and you recognize these patterns, and you say, okay, so this is going to be there for every degree. The problem is that you start finding weird guys. So these are not going to be included in this, and they're honestly exceptional. So you find 5, 4, 2, 2, 7, 6, 4, 2, 2. You find 7, 7, 4, 2, 2, and you find 9, 8, 6, 4, 2, 2. That's a particular monomial that is there, and this stops. This stops at this degree, which is the sum of all of these guys. I don't know what it is, but it's of the order of 40. And then you don't see anything else. But you kind of freak out because these are sporadic things that start appearing when you ask for higher degrees. And then why in the hell would it not appear a new monomial when you ask for degree, say 200? And my laptop could only get to degree 128. Okay, so I guess it's kind of kamikaze, but these are the horrible things that the computer spits. And you say, well, let's count these partitions. How do we count these partitions? So the first problem is this: the computer gave you a guess. These partitions are a basis. So count them. So to count them, you first find, you find a system of recurrences that these partitions satisfy. So recurrence equations. So that gives you a bunch of equations for the generating functions for these partitions. Of course, that's hard because of these 4 exceptional cases. So what you do is you divide the set of partitions in subsets. You write one equation for a system of equations that solves for each one of the subsets, and you solve that. And this leads to one generating function that counts these partitions. So you get to a generating function that counts these partitions because you solve a system of recursive equations. This leads to the following thing. So this is a theorem. It's well, I don't know how simple or not is this theorem, but let's put PTQ to be the sum of Pnm T to the m Q to the n, where Pnm is the number of partitions avoiding those terms above. So they are not multiples of the monomials in the ideal. With m parts. So it's exactly m parts. So this thing here is you solve for this, satisfies a system of recursive equations that you solve it. So that's very simple, and you get this expression. That this is called a fermionic sum. So this is a Q, this Q combinatorial coefficients, and this needs to be multiplied here by a polynomial like this. The form here is the only thing that matters. It's a linear term for t and a quadratic polynomial here for q, and then this division by this quantum coefficients. So any sum like this is called a fermionic sum. And that's it. That's what it is. So I have 1.5 minutes. So let me tell you the question that we have now. Sorry?
Why should this thing satisfy recursion relations in the first
Oh,
place?
that's a horrible thing to do. So what you do, and yeah, so that's a good question. So the way to do this is you split the system of these are horrible partitions. So you say, okay, so I'm going to split these partitions, this set of partitions, in 5 subsets. Those partitions that end up with a 2. Those partitions don't have a part that is 2. Those partitions that have a part that is 2, but don't have 2 parts that are 2. Those partitions that have a part that is 2, a second part that is 2, but the next one is not a 4, and so forth. So for those guys, you write a recursion. And the recursion is essentially you just add 1 to, if you give me a part like this, you add 1 to each one of these parts or subtract 1 from each one of those parts, and you can write it in terms of the other sets. So what I wrote is a system of 5 different subsets. So you get 5 sums that satisfy a system of recursive equations. We spent a year with computers also trying to guess what the solution is. And once you guess the solution, it's easy to prove it because it's an immediate system. So this was, I'm not admitting that this is a smart, no, something. Yeah, so this is not a smart thing. This is a brute force attack on a problem that is hard. We guessed what the solution is, and then the sum of those functions gave us this.
What is n?
Sorry?
What is n in P and M?
Sorry, what is m? Oh, so n is partitions of n. That's why I'm counting q to the n. And m is how many parts I have.
I see.
So if you see, so for Kac-Moody, this is typical. You put the charge, right? So you have some Cartan and you put a charge. For Virasoro, this is not clear. It's not clear what this t is measuring in the character of Virasoro. But now we have a candidate. After like fighting over this for a while, we have a candidate, and we know that if you put p of t is equal to 1, q, right? If we wanted to have to prove that it was an isomorphism, this should be equal to the character of Virasoro. And this you can compute because you know what the free fermions are. So this is a character of a Virasoro representation. And this is not. This doesn't seem to be easy to prove that that guy is there, right? So this is the kind of Rogers Ramanujan's type identities. What is the character of Virasoro? Let me give it for that central charge. This is one. This is a sum. So I'm going to give you a product on the other side. This is a product of 1 plus q to the 8k plus 5 minus 5. 1 plus q to the 8k minus 3. 1 minus q to the 8k. And this divided by 1 minus q to the 2k. So that's the character of Virasoro. This is an infinite product. This is an infinite sum. And we were incredibly happy when we spent a year trying to solve this recursive equation. And we said, well, once we have this equation, this is a conjecture, it should be trivially verified. You put it in a computer and it's true. This power series, when you put t is equal to 1, gives you the character of Virasoro. And you spent a few months trying to prove this identity and you can't because you don't work with polynomial identities. So this is what you do. You post this in Math Overflow and you send it to a bunch of experts. And this is when George Andrews, which is a co-author, comes in and says, hey, I know how to prove your identity, or at least I have a guess. And let me tell you what the guess is because it's standard. And I spent a few months trying to do that technique and I couldn't. And I swear I finished. So what you do is you find polynomials Pn and Qn such that Pn, so these are polynomials, no power series. The limit as n goes to infinity is this, and the limit as n goes to infinity of that guy is this, and Pn is equal to Qn. So you guess these polynomials. If you have many years as our co-author has, you can guess correctly these polynomials, and you prove that they are equal by proving that some of them are equal and finding a system of equations that they both satisfy. To find those equations, there's standard software. Once you guess the polynomials, it's easy to check on a computer. The problem is that the system of equations that these polynomials satisfy is a recursive system of degree 9. I don't remember if it was 9 or 15, but let's just be. So there's no smart way of proving this theorem. This is a computer that checks both. The recursive gives you the Grosvenor basis, another computer that checks this recursive system, and then you get the proof of that theorem. So you haven't learned anything, as I didn't learn anything from the proof of this theorem. But the point is that the Ising model has this kernel that is finitely generated by one guy. Let me finish just on that note that I put, of course, the same technique to work on a computer for the next case, which is P is equal to 3, Q is P prime is equal to 5. I put it in a 192 cores computer to compute the Grosvenor basis. It didn't converge after several months of computing. So I haven't learned anything from this problem, from solving this problem to solve any other minimal model. So I'd be happy if anyone takes over this kind of problems. Right, I'll stop right there.
Any questions from the online audience? And any in here? I have one weirdly specific tangential one. So you had this theorem about the ideal being finitely generated and parallel homology being finite.
Yeah.
Do you know? So that assumed that R was a commutative ring. Do you know if it would extend to graded commutative settings? Specifically, I have symplectic fermions in mind.
Well, so for symplectic fermions, you know explicitly what is the chiral homology. So there's nothing.
Which I would have thought was infinite.
Sorry?
But I would have thought that was infinite, at least.
Yeah, it's a Gaussian homology of a universal enveloping algebra, right? So this is in Bellinger and Drinfeld. So for chiral enveloping algebras, you know what the chiral homology is at every degree.
Yeah. So
okay. Yeah.
So yeah, that example seems to violate the. So
yeah, but that example, I think it already fails. Let me think. So for symplectic fermions, so you mean something like a beta gamma system or a BC system? Those two are very different. Beta gamma system is what you have in mind, right?
Yeah. Yeah.
So for the beta gamma system, so the problem here is that in degree 0, you have something that is infinite dimensional.
Yes.
And this is not covered. Yeah. So right. So my R, so already in degree 0, you have something that violates these conditions.
Thanks. Sorry for the slightly random question. Is there anything else? Let's thank Raimundo again.